Hi everyone, I'm Pierre and I'm a software engineer on Google Play.
Hi everyone, I'm Anthony, also a software engineer on Google Play.
And I'm Ibo, a partner developer advocate at Google.
So some of you may just be coming from the previous session at the amphitheater, which gave an overview of Google Play dynamic delivery and its new publishing format called the Android App Bundle and how this will make apps smaller. In this session, we will do a technical deep dive on this new publishing format. We will cover what it contains, how to build it, how to publish it, but also the different ways you can test it. We'll also cover how Google Play generates and serves the APKs to end users. So let's start with the format of the Android App Bundle. The Android App Bundle is a zip archive. It contains the files you're already familiar with in APKs, such as DEX files, Android resources, assets, native libraries. It's important to realize that the App Bundle and the APK are two distinct formats with two different purposes. The App Bundle is purely a publishing format, so it cannot be directly installed on a device. It also contains some metadata files that don't end up in the final APKs. They just help the tools build the APKs the right way. Finally, the format of the App Bundle is stricter than APK. We want to ensure that the tools can fully understand the files in the bundle so that they can generate valid APKs. Now, let's open up one App Bundle and look what's inside. So if you open up an App Bundle, this is what you should expect. So this should look familiar to a lot of people. Instead of reinventing the wheel, we decided to reuse some of the structure of APKs and only modify what we needed to better describe the files. So we'll briefly go through them. To start with, the App Bundle has support for having multiple modules, as you may have heard before. And we'll tell you more about modules shortly. For now, just know that the top-level directories in the App Bundle are the names of the modules. There is always a module named base in the bundle, and that's the one we're looking at here. The Android manifest is still present. In your project, it's a real XML file. In the APKs, you may know it's a binary format. In the App Bundle, it's compiled into a protocol buffer format, which allows us to transform it more easily. As opposed to APK, the DEX files are under a directory named DEX. The Android resources, the assets, and the native libraries, on the other hand, follow the same directory structure as in an APK. The only difference are the XML resources, which are also compiled into a protocol buffer format instead of the binary format. The file resources.pb is the resource table. It's the equivalent of the file resources.arsc that you may have seen in your APKs. It describes the resources present in your app and the targeting. The .pb extension meets in a protocol buffer format, which again makes it easier for tools to transform it before it's converted into its binary form in the APK. The assets.pb and native.pb files are the equivalent of the resource table for assets and native libraries. So they only exist if you have assets or native libraries, and they also describe the targeting of the files in their respective directories. As I've mentioned before, the resource table, the asset table, and the native libraries table describe the targeting of the files of your app. So let me explain what I mean by that. File targeting is the description of what type of device or user a given file is targeted for. It's a central concept in Google Play dynamic delivery, since understanding the targeting of files means we can serve to a given user only the files they need, and this is what allows us to make apps smaller. The App Bundle reuses the targeting that exists in APKs. You're already familiar with this, so I'll run through quickly. For resources, you specify, for example, HDPI in the directory name of your resource to target HDPI devices. Or you add FR to target French users. For native libraries, it's the same. You add the architecture to the directory. Again, nothing new here. The App Bundle works the same way. Now, we realize that for some of you, assets represent a big part of your app. So the App Bundle also supports assets targeting. We are starting with language targeting, and we will soon be adding texture compression format and graphics API versions. So we can serve only the relevant assets to the users and reduce further the size of your apps and games. This is how you would create a targeted assets directory. We are making use of the hash sign to identify an asset directory that has targeting. Then comes the key, which defines which dimensions we are targeting, for example, lang for the language, TCF for texture compression format, etc. And then comes the value associated with the key. Well, let's see some examples. Here's an example of a directory containing assets for users speaking French. This is another example of an asset directory targeted based on the texture compression format. Here, we're targeting devices that support the format etc1. Now that you know more about the app bundle format, I'll hand it over to Anthony, who will tell you how we use this to serve smaller apps to users.
Thanks, Pierre. Hi, everyone. So Pierre has just explained to you how we're changing the format of what you publish to the Play Store. And now I'm going to explain to you how we're changing the format of what we serve to users, and how we use this to deliver only what is needed for each user. Now we start with split APKs. So in Android Lollipop, we added a feature to the Android platform called split APKs. Split APKs allow multiple APKs to be installed on a device and behave as if they were part of a single app. These split APKs can be installed in different combinations on different devices, and they can be installed in one go up front or piece by piece. Now, a split APK has the same format as a normal APK. They can contain Java code index files, native code, resources, and assets directories. And once split APKs are installed, these can all be accessed as if they were in a single APK. And furthermore, each split APK shares the same package name and version code with all the other ones that are installed on a device. And they must all be signed with the same key. So now let's take a look at how we can take the Android app bundle and generate split APKs that we then serve to devices. So we start by looking in the app bundle and finding everything that is common to all the devices and putting those in a base APK. So this would include the Android manifest file and the DEX files, for instance. Then we generate a different split APK for each screen density. Each split will contain all the drawables that would have been selected by the Android framework on a device with that density. We can also generate a different split APK for each native architecture, containing native libraries of that architecture. And we can generate a different split for each language supported by your app, putting each language's strings in a different APK. Now, together we call these splits configuration splits, or config splits. Now, when we go to serve an app to a device, we only need to serve a subset of these splits instead of serving everything to every device. So say I have a Samsung Galaxy J5. We will install the base APK, as well as the XHDPI identity split, the ARM architecture split, and the English language split, because I only speak English. But it can get a bit trickier than that. Pierre speaks both French and English, and he specifies both of those languages in his device settings. So for his device, a Pixel 2 XL, in addition to the right density and architecture splits, we will serve both the French and the English language split to his device. Now, suppose Pierre then moves to Brazil and learns Portuguese. He might then add Portuguese as a language on his device. Now, when he does this, the Play Store recognizes this and will attempt to download the Portuguese language split for all apps that use splits on the device. And if the device is not online at the time, then we will download those language splits at the next opportunity. And so that's how config splits work. But as I mentioned at the start, splits are only supported on Lollipop and above. This covers about 85% of users at the moment, but most of you still target pre-L devices, which is great. And for these devices, the app bundle still allows us to achieve some of the size savings by generating standalone APKs containing specific densities and architectures. So instead of generating splits as we would do for L+, we would generate this matrix of standalone APKs. We briefly considered extending this to language splits as well, but we did some of the sums and it got a little bit out of hand. So for now, for pre-L devices, we have to include all the languages in each of the standalone APKs. Now, when we go to serve the app, we choose the best single APK for a device. So if we have my first Android device, a Galaxy Nexus, we would serve the HDPI ARM standalone APK. You might recognize this because this is similar to what you may have done in the past with multi-APK. But let's put this all together. The picture looks like this. And you actually don't need to worry about the details about how all these split APKs are generated or standalone APKs are generated. All you have to do is upload a single app bundle, and then Play generates the right splits and selects the right ones to serve for each device. And the dimensions we've discussed so far are only the beginning. Pierre discussed how the app bundle lets you target assets by graphics API, and we will soon generate config splits based on that. We'll also start generating config splits that take advantage of new platform features, and we'll start with supporting uncompressed native libraries on M+ devices. Now I'll ask Ibo to come up to take a look at how much we can reduce app size by using this app bundle.
Thank you, Anthony. Oh. Now that we know how Play serves split APKs to your devices, we're going to talk about the size savings with app bundles. We found out that, on average, apps published with app bundles are 20% smaller. And that is 20% savings every time your application is downloaded or upgraded. Now let's look at how we reached to this number. We analyzed all the applications in Play Store with more than 1 million downloads. And we found out that for strings, we can save over 95% of their size by using the language splits. For images, this is 45%. And for native libraries, we can save 20% of their sizes. This means if every app were to move to app bundles, we would save approximately 10 petabytes of data per day from app downloads and updates. That is 10 million gigabytes or 300 million music videos on YouTube. And on top of that, users could see an extra 300 megabytes of disk space for more photos, more apps, or more music on their devices. So now let's look at actual size savings that some of our early access program partners saw. We're going to start with Twitter. Twitter were already publishing with multi-APKs before, with architecture splits. However, their application is translated into a lot of languages, and it supports multiple screen densities. They still get lots of savings with publishing with app bundles, which is 20% decrease in the size. Plus, they don't have to serve with multi-APKs anymore. The next one is Text Plus, which wasn't using multi-APKs before. With app bundles, they achieved 26% size savings across all dimensions with app bundles. Jomo's app is half of its original size. And this is because they have a large native library and they supported multiple architectures in a single APK. Now let's look at how we can build an app bundle, and you can start saving now. The latest Android Studio 3.2 Canary has full support for building Android app bundles. Now we're going to see a new option to build a bundle in the Build menu. Generating a signed app bundle is easy as well. You're going to just select your app bundle, app module, product flavor, and build type, and Android Studio is going to create an app bundle for you, signed, which is ready for publishing. For those who prefer command line or wish to integrate with automated build systems, the new Gradle Android plugin provides a new set of tasks to build Android app bundles. As you remember, this is what you use, the assemble task on the command line to create the APK. Now for app bundles, you're going to switch to the bundle command. Similar to the assemble tasks, Bundle tasks also allow you to build a specific flavor of your application. Once the bundle task finishes, it's going to create an app bundle in the output folder with the flavor and the build type chosen. The build artifact is called bundle.iab. Bundle tasks are compatible with the signing configs in your build.gradle files, and with a single Gradle task, you can produce app bundles that are signed and ready for publishing. And also, with app bundles, Play will automatically split your application into architectures, screen density, and language splits by default. You don't need to do any configurations. However, we still want our developers to have full control over their splits. So if for any reason you would like to disable splitting by any dimension, you can do so by using the newly introduced bundle block here. Now, Pierre is going to talk about how to publish your app bundle in the Play console.
Thanks, Ivo. All right, so you have built an app bundle. Now let's look at how you can publish it on Google Play Console. First, you must enroll in App Signing by Google Play. For those who remember, we launched this program at Google I/O last year. When enrolling, you securely transfer your release key to Google Play. Play then uses this release key to sign the generated APKs on your behalf before serving them to users. But note that if you keep uploading APKs on your production track while you test the app bundle in the test track, Play will not resign the uploaded APKs. And we did this so you can feel confident trying the app bundle on a small audience first without affecting your current production users. Once you're enrolled, you can manage your releases just like you did for APKs. Create a new release, drop the app bundles in the same location where you currently drop APKs, and wait for the upload. Once uploaded, you can review your release and roll it out. That's it. And I can't stress this enough, no more multi-APKs to deal with. Play Console has created in the background all the APKs for the supported devices for you. Now, you have uploaded your app bundle and Play has done all the heavy lifting for you. Great. But wouldn't it be nice to be able to have an overview of what Play has generated? Well, we have built a new tool in Play Console called Bundle Explorer. Bundle Explorer lets you navigate your uploaded bundles. Let's have a look. On the first screen, you can see at the top right corner the size savings you gain by publishing a bundle. Here we saved over a quarter of your app. Of course, this is different by device, so we calculated this using a popular device configuration. You will also find below the list of device configurations and the total size of the APKs served to those devices. You can even click on View Devices and see which devices are in each bucket. You can even search for any supported device by name to download the set of generated APKs that is served to that specific device. This will be super helpful when you get, that bug report on that specific device, and you want to get exactly what the user has gotten, what the APKs were served. So you just search for the name, click download, and you'll get the set of APKs that Play has served. Of course, we haven't forgotten all of you who use our publishing API. Uploading app bundles is also available using our API today. You will find all the documentation at developers.google.com/Android-publisher. I'll now hand it over to Anthony.
Thanks, Pierre. So we've now learned how to build and publish an Android app bundle. But before we finalize a release, we'd still like to do a round of tests. However, we've seen that the app bundle on its own is not installable. So how do you test it? First, we note that during development, you can install APKs built from the app bundle directly from Android Studio. So you don't need to do anything here. However, for QA teams, we know that they don't always have access to the source code in Android Studio. So let me talk you through the story of 3 developers, Alice, Bob, and Claire, and how they choose to test their app bundle with their QA teams. So let's start with Alice. Alice uses the newly released internal test track from the Play console. The internal track is similar to alpha and beta tracks that you may already be familiar with, but it differs in that there is almost no delay between the upload of the bundle and the update being available on the tester's devices. Really quick turnarounds for your QA testing. Going through the Play console, Alice has the confidence that what the QA team will receive on their device is byte for byte equal with what end users will get when you push your release to production. And let's see how Alice sets this up. Really simple. So Alice creates a list of emails of up to 100 QA testers that are eligible for the internal test track. Her QA testers follow the opt-in link, and then they'll receive the bundles that are uploaded to the internal test track. That's it. But we know that not all of you have access to the Play console during your QA cycles. So let's hear from Pierre about Bob's story.
Indeed, Bob doesn't have access to the Play console. He prefers also to test things locally on his machine before uploading anything. But he still wants to test what the users will get. So how does he do that? Well, to generate APKs from the bundle, Play uses a new tool called Bundle Tool. So for Bob to reproduce locally the builds, he can simply download Bundle Tool and write a few simple commands. Bundle Tool has a command called build APKs, which takes an Android app bundle and creates what we call an APK set archive. This APK set contains a collection of APKs ready to be installed on devices. Another command called install APKs takes that APK set archive, extracts the APKs, and installs them on that device. Now let's see some real command line work. So here's the command written by Bob, calling build APKs, passing the app bundle, and saying where he wants the APK set to be created. And by passing the flag connected device, Bundle Tool will build APKs just for the device currently connected to his machine. And if Bob wants to generate APKs, say, for someone else in his team, but without having the physical device at hand, he can still provide a file that contains the specifications of the device in a JSON format. And you can see here an extract of such file, which provides the information about the ABIs this device supports, the supported languages, the screen density, and the SDK version. Bundle Tool has also a command to generate such device spec file. So you don't have to find the device spec online, or you don't have to write it yourself. You just run this command, and it will generate this file for you. Also, because Bob wants to install these APKs on a device, the APKs need to be signed with a private key. So he passes the path to the key store. All the APKs contained in the APK set will then be signed and directly installable on Bob's device. And here's the invocation of the install APKs command, which extracts the APKs from the APK set and installs them directly on the connected device. Easy. So that was Bob and his local testing. Now, Ibo will tell you Claire's story.
Claire is working for a medium-sized company, and they set up a continuous integration tool to build their application. Every day, the QA team pulls a nightly build of the application, installs in multiple devices, and tests if the application is working correctly. Now, Claire wants to help the QA team, and she uses the bundle tool again to generate the APK set in the CI. She uses a command that's very similar to what Bob used earlier. But this time, she omits the device spec flag, and she generates an APK set which contains APKs for all possible devices. Now, the QA team will just grab the APK set from the CI. They're going to connect the device and run the install APKs command. Bundle Tool now will read the device configuration from the attached device, will extract the APKs that matches this configuration from the APK set, and then install them onto the device. This is the same selection that Play does when serving APKs for a given device. One more thing that Bundle Tool can do is to generate a universal APK by passing the universal flag. The universal APK is a single APK that contains the file, all the files that matches all the devices. Because of that, it can be installed in any device. Well, it really doesn't represent what your users will receive when they install your application from Play Store. However, this is a convenient way to pass an APK to a user when you don't know what device they are running. Bundle tool is also the tool used to build an Android app bundle. And Gradle uses it behind the scenes. We're going to work with the other build chains, tool chains, to integrate build tool so that you can build an Android app bundle regardless of any tool chain you may be using. And finally, we want to be transparent about how we generate the APKs we deliver to your users, which is why we're open sourcing Bundle Tool. You can go today to github.com/google/bundle tool to download an executable or build it from the source. Now, Pierre is going to talk about another way to make your applications even smaller.
Thanks, Ibo. With Google Play Dynamic Delivery, we're also introducing a new way to break up your app into separate features and deliver only those that are needed for each user. Suppose you have a recipe app and you want to keep the initial download small. You observe that while all your users like to browse for recipes, only a small fraction choose to actually add a new recipe. And you notice that this functionality takes up significant space in your app. What you can do is break that feature out into its own module and serve it only when needed. We can see how it looks for a user here. Let's open the app. And so when the user wants to add a recipe, he clicks a little plus at the bottom. And you can see that in the background, the module is downloaded and installed. And just after a few seconds, the module is ready to be used. So, which parts of your app should you break out as separate features? If only a small fraction of your users use that feature, that could be a good candidate, especially if that feature takes up significant space in your app. Finally, consider if your users can wait a few seconds before using the feature. Once you've decided which feature to create, this is how it should look like in the app bundle. In addition to the base directory, there are now also separate directories for each of the modules of the app. The format of these directories is exactly the same as the format of the base that I covered earlier. And this is the APKs that Play would generate from it. For each module, we will produce a set of splits consisting of a feature split and config splits for that module. Anthony mentioned earlier that split APKs were only introduced with Android Lollipop. To support pre-L devices, you can mark modules to be fused, and Bundle Tool will generate a single APK with a specified module merged together. Now that we have covered how dynamic features work, let me hand it over to Ibo, who will show you how to create them.
Thanks, Pierre. To create a dynamic module, all you need to do is download Android Studio 3.2 Canary and use the dynamic feature wizard included. Click on the new module in File menu, choose the dynamic module. After typing in your module's name, Android Studio is going to create a new dynamic module for you. You can also do the same thing manually by editing the manifest and build.gradle files. You're going to start with the manifest of your new module. The first step is to declare this module as a new split APK of your app. To do so, you're going to add the split attribute in the manifest tag and give a name, which is VR_viewer in this example. The next step is to add a module tag, which is going to declare a module, and you're going to give a title to the module. This tag is used by Play Store to identify the modules of your application. Next, you declare this module as an on-demand module by adding the on-demand attribute. This means that this module is only going to be delivered to the user's device when the app requests it from the Play Store instead of delivering it at install time. Of course, We now know that on-demand modules are only supported on L+ devices. So if you choose to also provide this module in pre-L devices, you're going to add the fusing tag to instruct Play Store to include this module alongside the base module at install time when delivering to pre-L devices or in the universal APK. Now let's look at the build.gradle files. We're going to start with the dynamic module. The first thing is that we're now using a new plugin called com.android.android-feature. The second thing is we add the base module as a dependency to this module so that we can access the functionality included in the base module. The only change required in the build.gradle file of the base module is to add the dynamic features list and put all the dynamic module names into this list. This is to instruct Gradle to make the resources stored in the base module available to those dynamic modules. Now, Anthony is going to show you how you can use those modules with the new PlayCore library.
Thanks, Ivo. So let's take a look at how you go about requesting on-demand modules to be installed when you want them to be installed. So in order to interact with the Play Store, we are introducing a split install API as part of a new library called the PlayCore library. Now, the PlayCore library is a Java client library that communicates with the Play Store via IPC on the device. And then the Play Store communicates with Play servers to download these on-demand modules when you request them. Let's take a look at a bit of the code. The API is structured using the same task framework that you're probably familiar with from the Google Play Services APIs and Firebase APIs on Android. Installation of splits is coordinated by a class called the Split Install Manager. You construct a request with all the modules that you wish to download, and then you invoke start install to trigger the Play Store to download the splits required for those requested modules. The API also allows you to listen for updates throughout the download and install process. You can use this to display progress, the download progress and the install progress to your users while they are waiting for the on-demand feature to download. You saw this in the video that Pierre showed when it was downloading the add recipe module. For large modules, you'll need to obtain user confirmation prior to the download via the Split Install API. You'll need to do this whenever the app requests more than 10 megabytes of on-demand modules to be downloaded. However, there is an alternative option for installing these modules, which if they aren't required immediately for immediate use. And we call this the Deferred Installation API. If you use this simple one line to request a deferred install of a module, then the module will be downloaded at a convenient time for the user. So this is generally when the user's not using the device and it's charging and it's on Wi-Fi. And because of this, we allow you to install larger modules via this API without requiring user confirmation, up to 100 megabytes. And so this is a really user-friendly way to download large on-demand modules for your app. You can also use the Split Install API to manage your on-demand modules. So you can see which modules are currently installed, and if your user no longer needs that module, you can request for the module to be uninstalled, freeing up the precious disk space for your users and reducing the footprint of your app on their device. Now, when you go and install an on-demand module, on N+ devices, the app does not need to be restarted. So code is available immediately upon the install completing, and new resources and assets are available once you refresh your context object. However, on Android L and M, installing splits requires the app to restart if you want to install them properly. But to avoid this, we've included a split compat library, which emulates the installation of a split on L and M until the app goes into the background and we can properly install it. And so this split compat library means that your app doesn't need to restart, and all the things inside this, or almost all the things inside this module, are immediately available to your app. You can set this split compat library up in a very similar way to how you might be familiar with setting up the multi-dex library in your apps. Finally, when you release an update to your app, Play will automatically update both the base module and any on-demand modules that are already installed. So the versions of your modules that are on a device are always in sync. They're always at the same version. And partners tell us that this is something that they really like about this model. All right, so let's wrap this all up. Starting today, all developers can build Android app bundles in Android Studio 3.2 Canary. And they'll be able to publish these on Play to all users. So I encourage all of you to try this out and see how much smaller your app can be just by switching to the Android app bundle. Now, we will be rolling out modularization to developers over the coming months. From today, you can start building modularized apps in the Studio Canary, and you can publish them to the internal and alpha tracks within the Play console. But we'll be opening up publishing in production tracks as a beta over the coming months. And if you're interested, you can register your interest in modularization at the link provided. And with that, thank you everyone for coming. If you have any questions, you can grab us afterwards. I don't think we have time right now. Or you can grab us over the next couple of days in the Sandbox C, just behind the stage. And then thank you. Have a great I/O.